All right, folks, we're going to jump into some circular motion problems with Newton's second law, and here we go. So we're going to do 3 problems today. First one is a dip in the road problem. I set up this problem in the other video, but I want to go through it again. So when we talk about like dip in the road or top of a hill or even the loop, we generally only talk about the top, the exact bottom, or the exact sides. And any calculation typically just happens with either the top of a circle or the bottom of a circle. And we do that because things are simpler. And they're complicated enough for AP Physics, but they're simple enough for us to analyze them really easily. So into the circle is positive. I drew my arrows a different length. Maybe by now you're like, okay, well, I know that this car is getting kind of squished into the road there. I know that the acceleration has to be toward the center, and so the net force has to be up in this situation. So the normal force has to be greater than gravity. That is supported by this 110%. It says it experiences an apparent weight that is 110% its actual weight. We can turn that into an equation. Fn is the apparent weight. It is, meaning equals, 110%, that's 1.1 times its actual weight, which is mg. So the normal force is 1.1 times the weight of this car. And that happens due to the upward acceleration that we see here. So we're going to start with our usual net force in the centripetal direction equals mass times acceleration. The question we're answering is with what speed should the car travel so that happens. The greater the speed, the greater the acceleration, and so the greater the net force. That's the higher the normal force goes. Okay, so normal force minus gravity equals net centripetal force, which is mv squared over r. All right, so I'm solving this for v. I'm going to start by plugging in my little ratio here, essentially. So the normal force is 1.1 mg. I take away from that mg, and again, that's equal to mv squared over r. All right, so this equation, every term in this equation has mass in it, and so I can divide this entire equation by m, and that m will go away. I'm left with 1.1 g minus g. Well, 1.1 g minus g is just going to leave 0.1 g behind. And then on the right-hand side, that's equal to v squared over r. All right, so the acceleration of this car is 0.1 times little g, so 0.98. When I solve this, 0.1 times 9.8 equals v squared over the radius, which was given up here as 14. When I solve that, the speed is going to be 3.7 meters per second. If this car goes faster, its apparent weight will increase. If that car goes slower, its apparent weight will decrease. A question comes up sometimes of like, shouldn't there be horizontal forces? Shouldn't there be friction or some driving force? We are going to assume that this car is like coasting through this hill at a constant speed, and that if there are horizontal forces, they would cancel. Okay, next one is a friction one. Car has tires that have a coefficient of static friction of 0.95. What is the maximum speed that a car can make a 17-meter radius turn without sliding? So this car is going to be moving through this turn, and because we see that this turn is curved, there's going to be centripetal acceleration toward the center of it. We're going to take the view from behind the car. So we're going to imagine that we're like there, looking at the car in front of us as if we're following the car on the turn. That means that gravity is going to point down, the normal force is going to point up, and then, we've talked about this once before, static friction is going to point toward the center of the circle. So this is an important time to talk about Newton's first law. If you are going through a turn and your tires lose their traction completely with the road, you will move in a straight line tangent to the circle based on the moment you lost traction. So this straight line is very important. If this static friction force doesn't exist, then all of a sudden the car is moving in a straight line in whatever direction it was going when that static friction force disappeared. All right, so let's find this maximum speed. So we'll start with the net force in the centripetal direction. Because this is friction, I'm also going to talk about the net force in the y direction. That's going to be 0. And then I'm also going to do a little bit with the friction equation. And so I do recommend that when you're doing any sort of calculation with the coefficient of friction, that you set this up the same way. All right. So the net centripetal force is the static friction force, and that's equal to mv squared over r. This means because I need to know the maximum speed, I need to know more details about static friction. So I'm going to work my way across right now. The net force in the y direction is 0. This is a car that we're going to imagine is on flat ground, so the normal force is equal to mg. I'm not given the mass of the car. That's kind of been a theme of this unit, and so I'm not going to be able to calculate that. But I can take this and give it to the friction equation. So the static friction force is going to be equal to mu sub s times mg. Now that I have found this expression, which is fairly common but not universal, I can bring it back to this equation. And I can say mu sub s times mg equals mv squared over r. So, you might find yourself getting stuck in these problems. When you're doing friction problems, you essentially have 3 equations that you need to manage: the centripetal or x direction, the y direction, and then the friction equation itself. You can show your work in a bunch of different ways, but I like this one because it shows me my options. All right, both terms in this equation have mass, so I can cancel that, and I can solve it for v. If I were to solve this equation for v, it would be the square root of mu times g times r. So not coincidentally, 3 values that I know at this moment. So that speed is going to be 0.95 times 9.8 times 17, and then the square root of that. That speed is 12.6 meters per second. So what makes that speed the maximum speed? Well, if the car was traveling any further, then I would have exceeded the maximum static friction force. So I didn't mention that. This is the maximum. The only evidence that you might have is that I use an equal sign for static friction, and that means that I'm using the maximum. So this is the speed that pushes the friction force to its limit. Anything higher and it would start to skid. Okay, and then the last one is the loop-the-loop question. Motorcycle, I am definitely going to draw a car instead of a motorcycle because it's less challenging for me. The motorcycle is traveling through the loop, and so we're going to draw a force diagram for that. Now I know that gravity is down, and I also know that the surface that this motorcycle is on is above the motorcycle. And so I'm also going to add the normal force into that diagram. And then down is the positive direction. So jumping into that, net centripetal force is mass times acceleration. The 2 forces point in the same direction and in the positive direction. And so I add them together. All right, and then we come to the qualifier of this problem without losing contact with the loop. So the slower, so let me talk about this equation. This mg can't change. R can't change. So really, v and fn are the only variables in this equation that can change. The faster that the motorcycle drives, the bigger the normal force. The more the normal force is going to push down on the motorcycle. If I want this motorcycle to be at the limit where it's about to lose contact with the loop, I have to imagine that the speed goes down further and further until this normal force is as close to 0 as possible. So we make it 0, and that will be our limiting case. Now we're left with mg equals mv squared over r. Now, if the normal force was there still, I couldn't cancel mass. But because we set the normal force equal to 0, I can now cancel mass. And my speed that I can travel is the square root of g times r. Just look at how similar that expression is to the friction one that I came up with, square root of mu times gr. So this is common stuff for circular motion. So that speed is going to be the square root of 9.8 times 8, and it is 8.9 meters per second. All right, so that's an intro. I know I solved for the same variable 3 times in a row, but the setup is the same idea for each one. Just follow your Newton's second law pattern with this new v squared over r term, and you should be okay.